Hello. In this video we will talk about work. At least we'll talk about the kind of work that physicists like to talk about. We said that energy is conserved, which means that it cannot be created or destroyed. It can, however, be transferred to other forms, or to other objects. Energy can be transferred a bunch of different ways, like through heat or through light. In this course, we will discuss almost entirely one form of energy transfer. We call that work. Work is when energy is transferred by the application of a force. It should make some sense to you that applying a force will change the energy. After all, the application of a force can speed up or slow down an object, which will change its kinetic energy. Work is calculated with this simple formula. Work equals the force times the distance. So, if we apply a force of 10 newtons over a distance of 10 meters, then the force will have done 100 joules of work, which means that we have transferred 100 joules of energy either to or from the object. Let's look at the following example. Imagine I have a block of mass 2 kilograms sliding along a surface at 4 meters per second. The surface does have friction though, so there is a frictional force opposing this motion. Let's say it has a force of 4 newtons. How far will my block go before it comes to a complete halt? Well, our question really is, how much distance before the kinetic energy of the block is reduced to zero? Because when the kinetic energy is zero, the speed is zero. So let's set up the following equation. At first, the only energy we have is the kinetic energy of our block. Afterwards, the kinetic energy of the block will be zero, but that kinetic energy has to have gone somewhere. In fact, it was all transferred by the work of friction, which equals the frictional force times the distance traveled. What type of energy it was transferred into, or where it went, doesn't matter for our problem right now. So afterwards, we just have the work done by friction. Now, because energy is conserved, we can equate the before and after energies to each other. So now we just need to solve for the distance traveled. So we divide both sides by the frictional force. Plugging in the numbers, we get this expression. If you do the arithmetic, that all turns into 4 meters. So that is how far your block will slide before stopping. Now, you might be wondering, why do I have to learn this whole energy thing? Couldn't I have solved this problem with forces and accelerations? Well, you are correct, you could have. But it would have taken a lot more effort. In fact, I dare you to go ahead and solve the same problem with forces and accelerations. Seriously, give it a shot. In some cases, you won't be able to solve a problem with forces at all, at least not without running a simulation on a computer. By considering energies, however, you may be able to solve a whole new class of problems. Now, I should point out that the work equation is not quite so simple as force times distance. After all, what if the force changes at different points along the path it travels? Which force value should you use? We will usually be working in cases where the force is constant, so we won't encounter this problem. However, in the event of changing forces, you should know that we can either use calculus or a fairly simple computer program to compute the work done. Now, let's look at one more example. Imagine I have a box sitting on a frictionless surface. I want to get this box moving, so I start tugging at it with an applied force like this. After I drag it 10 meters, how fast will it be moving? Assume that I am unable to lift the box off the ground by pulling like this, so the box does slide along the surface. So before you run off to try this problem yourself, there is another part of calculating work that I have been hiding from you. We can break this force vector down into two parts. There is a force component that is pointed in the same direction as the displacement of the object, and there is a component that is perpendicular to the displacement direction. The work is actually the parallel force times the displacement. We can ignore any perpendicular force. There, no more secrets. Now you can go try this problem yourself. So let's work this problem out. The final speed is dependent on the final kinetic energy. So let's write out our energy equation. At first, there is no kinetic energy, but there is work energy from my pulling that is in the system from the start. After I get it to 10 meters, the box now has some kinetic energy, and all the work from my pulling that we care about has already been spent. These two values equal each other, since the energy is constant. So let's work on the left side of the equation first. What is the work done by my pulling? Well, the distance is definitely 10 meters. But what is the parallel pulling force? We'll have to do a bit of trig here. If we use the cosine relationship, we see that cosine of 60 degrees will equal the parallel force component divided by the magnitude of my pulling force. Solving for the parallel force, we have the magnitude times cosine 60. Cosine of 60 is 1/2, so you'll find that the parallel component is 10 newtons. So going back to our equation, we have 10 newtons times 10 meters, which is 100 joules. Therefore, the kinetic energy of the box is 100 joules, and I'll leave it to you to solve for the speed of the box if you want. Perhaps you were a bit confused about how I came up with those energy equations from before. It can be a bit confusing to know when we should consider work in the initial energy or when it should be in the final energy. For that reason, I will show you a helpful equation. This equation says that the work done is equal to the change in kinetic energy, or the final kinetic energy minus the initial kinetic energy. For instance, if we have an object that initially has 100 joules of kinetic energy, and then after something happens it has 200 joules of kinetic energy, we can calculate how much work was done. The work done here is 200 joules minus 100 joules, which is positive 100 joules. When the work is positive, we say that work is done on the object. This means that energy has been transferred into the object's kinetic energy. But when work is negative, we say that work is done by the object. This means that energy is transferred from the object's kinetic energy. That energy either goes into a different type of energy or into a different object. Let's summarize what we learned before we end this video. We learned that work is a form of energy transfer that occurs due to the application of a force over some distance. In fact, the formula for work is given by work equals force times distance. More accurately, we only care about the component of force that is in the same direction as the distance traveled. So we will rewrite our work equation like this. Finally, this equation only works if the force is constant over the distance traveled.